we have studied all of the different types of functions that we need to be familiar with going forward. So we've studied all the different algebraic functions, ways of identifying characteristics about those functions, right? Like x-intercepts correspond to real zeros, talking about any discontinuity, points of discontinuity, just from like the way that we think about discontinuity being if you have to lift your pencil as you're tracing the graph, then it's a type of discontinuity, whether that's removable or non-removable. Determining if a function is increasing or decreasing, again, reading the graph, we're thinking about as x is getting larger, what's happening to the y values of a function on an interval. We've also looked at graphs from like a functions from a transformation perspective, thinking about a parent function and then what is happening to the parent function to result in the graph of a given function. And we did that also with like the transcendental functions, so exponential and log functions and the trig functions. So we've studied all the families of functions that we've needed to study, and now we're here. Okay, so limits are going to provide us with a new way to analyze a given function's behavior, like another way to identify different characteristics that we haven't previously really been able to talk about with a function. Well, actually we kind of have, but now we'll have a more rigorous definition of like continuity, increasing, decreasing, and so on. Does that make sense? The different limits, though, require you to look at a function from a different perspective. Like up until now, we've been so concerned about like what is happening at a specific point, or based on an input, what is the output of a function, right? The idea behind limits is thinking about, okay, as x approaches some number, or maybe positive infinity or negative infinity, what is the function approaching? From both sides, from one side, or like as x approaches, we've talked about this before when we've talked about end behavior, as x approaches positive infinity, what does it seem like the function is approaching? As x approaches negative infinity, what does it seem like the function's approaching? But like then what does that tell us about the function? What does that tell us about the graph of a given function? Okay, so kind of keeping in mind for limits, what happens to values of a function, or like the y values of a function f, as x approaches a real number c? So the informal definition of the limit of a function is if the values of f of x become arbitrarily close to L is just a number, as x gets sufficiently close to c but not equal to c, then we're able to say that the limit of f of x as x approaches c is L. And all three of these statements say the same thing. You guys are familiar with this notation. Do you guys remember when we used this notation? Yeah, when we were talking about end behavior, right? We were like, okay, as x approaches positive or negative infinity, what is the function trending towards? Like, is it approaching a number? Is it approaching positive or negative infinity? We talked about like end behavior asymptotes, giving us kind of a description of end behavior. But we can also think about, well, like as x approaches a number, like a finite number, as x approaches 2, is the function approaching a number? Is it approaching positive infinity? Is it approaching negative infinity? Is it approaching one value as it approaches whatever that number is from the left versus approaching from the right? So there are 3 different cases for when we say a limit exists, okay? And understanding these 3 cases for when this statement is true is important. It's also important to understand whenever this statement isn't true. So I'm going to go through right now the 3 cases of when we say a limit exists. And the first one is pretty straightforward. So I'm going to draw, how do I want to do this? I'm going to draw 3 graphs here that will look very similar. So I think I'm just going to draw quadrant 1. I'm going to copy and paste this 2 other times. Paste, paste. Okay, so I'm drawing the 3 different, or examples of the 3 cases whenever the statement above, so the fact that the limit as x approaches c of f of x is equal to L. So the first case is, let's say that this is the function f. Let's say this is x equals to c, and this is L. Meaning the point C comma L is on the graph of f. This is the first example of when that limit statement would be true. And it's when thinking about f of c is equal to L. So like the function value matches the limit. So the function's value matches what it seems like the function value is approaching. And you're like, well, yeah, duh. The next situation where the limit would exist, or the next case where the limit would exist, is where, let's say we have similar function f. But let's think of this like there's a piecewise. So let's say like the function is equal to some rule for all real numbers except for whenever x is equal to c. Okay, so this, let's say this is still x equals to c. This is L. But f of c is some other value. Like there's a point. So whenever x is equal to c, f will be equal to f of c. So that point is c comma f of c. Again, an example of this would be like a piecewise function. Okay, so this case where the limit exists still, f of c is not equal to L. Now, if we were tracing our fingers along the graph, like getting in the neighborhood of x equals to c on the graph, wouldn't we want this function value to be L? Like if we trace along the graph, approaching c from the left-hand side, it seems like the function values, the y values, are approaching L. And as x approaches c from the right-hand side, it seems like the function values are also trending towards L. However, the function value is not equal to L. The function value is whatever this value is up here, and that's okay. The limit still exists because as we're getting really, really close to x equals to c on both sides, the y values of the function values, are trending towards L. So that means that the limit exists. The function is not continuous at c. And we've talked about continuity. Like what type of continuity would this be an example? Discontinuity would this be an example of? Remember there were the 2 classifications?
Continuous.
Removable.
Oh yeah.
So which one is it?
It's
removable, because we would want to think about removing that discontinuity just by filling in that one point with C comma L, right? You just have to think about lifting your pencil for a second, and then you're able to continue on. So the graph is trending towards L. The function values are trending towards L as x approaches C. It's just that the function value does not actually match the limit value in this case. But the limit still exists. Okay, third case, similar to the previous one, is just if f of c is undefined. So I'm going to draw a very similar graph. So this is still f, this is f. Right, so this is x equals to c, this would be L. But f of c is undefined, because there is, again, a non-removable discontinuity, or in this class, what have we referred to that as? A hole. So if there's a hole in the graph, right, as x approaches c, the function values are still trending towards L. The y values are still trending towards L. So we would say that the limit exists even though the function is undefined at x equals to c. So again, limits are not, like a limit existing is not dependent on a function value. It's dependent on what does it seem like the function values are trending towards as x is approaching a certain number, or a certain value. So in this section, we're going to talk about,
Are they playing like Stick It To Me?
I don't know.
You're not allowed to.
Well, it's PE.
You guys, Michael's sister got me out yesterday.
I
She
saw.
tricked me.
How?
She tricked. Okay, so I sent them. I'm teaching the summer bridge class this summer. And I sent out an email. I like set it up for her. I sent them an email yesterday morning. So like, it wasn't weird that she came here to talk to me yesterday after class. And she's like standing in the door. She's like, can I? And it's like acting kind of nervous. And like, we're recording this, but that's okay. Like she like kind of like draws me out to talk to her about it, and like she seemed like she was like concerned about something. And then she goes, I'm really sorry about this. Sticks it on my back. I was like, no! Although it was okay because I was pretty, it like made me really anxious all day yesterday. Like knowing there was someone out there looking for me. And then she got my person like super fast after that.
She's currently
Yeah, she has the most pillows out of it.
I'm not
I'm
not surprised. I'm not
More?
surprised.
Oh my gosh.
Avery was the one you're going to say.
Quite the actor, but I totally did set it up. Like it wasn't weird. She got lucky. Like it wasn't weird that she was like coming to talk to me. Oh man, but it's okay. Okay. Anywho, so in this section, you guys, we're going to talk about estimating limits. So estimating what the value of a limit is. Numerically and graphically. So numerically, that means like thinking about creating a table of values and looking at what it seems like the function values are trending towards, or if there is a trend. And then graphically is exactly what it sounds like. You look at the graph to determine what it looks like the limit would be, like what it looks like the function is approaching. So numerical approach, graphical approach. Now, we can do better than just estimating limits. So we can think about evaluating limits analytically, and an analytical approach would be either using algebra, which we will maybe start next class, maybe not, I'm not sure, but it's what we would kind of like lead off with in the fall. or using calculus. Okay, so limits can be evaluated analytically using either algebra or calculus. But for now, we're going to try and understand what a limit is by looking at limits from a numerical and a graphical perspective or approach. So I want you guys, filling in the table, you should have gotten, what, 0.75, 0.9, 0.99, 0.999, right? So choosing values that are getting closer and closer and closer to 2 from the left, but then 2 is undefined. So at x equals to 2, that function, that rational function is undefined. At 2.001, we get 1.001, then 1.01, 1.1, 1.25. Now the first question here that asks, what seems to be happening to the values of f of x as x approaches 2 from the left side? Do you guys remember this notation? As x approaches 2 from the left.
Oh.
We talked about this when we talked about vertical asymptotes and the behavior of a function at a vertical asymptote. Remember?
Foreshadowing.
So as x approaches 2 from the left, it seems like f of x is approaching what? Right? So this would be from the left side. It seems like f of x is approaching 1. Are we all in agreement about that?
Mr. Hamilton reference.
What was that? I don't understand.
I'm in agreement. I am in agreement.
Yeah.
Ah,
Yeah, he says it.
okay.
He's never said you're right or you're wrong. He's always been.
Next question. As x approaches 2 from the right, we've used this notation before. As x approaches 2 from the right, f of x seems to be approaching also 1. Interesting. But what is f of 2? Undefined. Okay. So in this case, the function is approaching the same value from the left and the right, but the function is undefined at x equals to 2. So like graphically, what would we say occurs at x equals to 2? We could even, you guys have all these tools in your toolbox currently. Don't you know how, couldn't we factor the numerator?
Oh.
Was that x minus 2, x minus 1 over x minus 2? So we have that common factor. So the graph will actually look like the line y equals to x minus 1, but it'll be undefined at x equals to 2, and there will be what we say is a, good, so there will be a removable discontinuity yeah, kind of more specifically, a hole. Because if we typed that into, here, if we type that into Desmos, so y equals x squared minus 3x plus 2 divided by x minus 2, right? We can see, oh, it just looks like a line. You wouldn't expect this graph to have like kind of an interesting equation. However, if we zoom in, you can't see it, but there we go. We can see At x equals to 2, the graph is undefined, but we can clearly see the graph is approaching from the left as x approaches 2. The graph is approaching 1 because the function values are getting closer and closer to 1, like increasing. And then from the right, the function values would be decreasing and approaching 1 from above. So yes, we say that a hole occurs at x equals to 2, which is a removable discontinuity. Okay, so based on like putting this all together, what does f of x seem to be approaching as x approaches 2 from both sides? So we can say as, oops, that's not what I want. As x approaches 2, where if there's no notation in like that exponent position, it means as x approaches 2 from the left and the right. F of x seems to be approaching 1, which can also be written as the limit as x approaches 2 of this rational function is equal to 1. So even though the function is not defined at x equals to 2, its limit as x approaches 2 is equal to 1 because the function values are trending towards 1. Are we following this okay? Questions? Okay. We've kind of been referencing these one-sided limits already. But we can talk, sometimes it's appropriate to only talk about a one-sided limit, and we'll get more into that later. But there are times whenever you really do have to think about, okay, well, what's happening from the left? What's happening from the right side? So what's the left-handed limit? Does it exist? Does it not exist? What's the right-handed limit? And the notation is the same that we've been using for indicating from the left or from the right. So whenever we were talking about vertical asymptotes in semester 1, and we used this notation to be like, okay, well, as x approaches this number from the left side, is the function approaching positive or negative infinity? And remember we did like test values to see? It's all up there, right? So left-sided limits, right-sided limits, and then for the standard two-sided limit to exist, so like, for example, the limit from above, the one-sided limits both have to exist and be equal to each other, so they have to match up. So this leads us into estimating limits graphically. So from reading a graph, determining whether a limit exists, if it exists, what that value is, or if it doesn't exist. So this first one, looking at as x approaches 0, that negative indicates we're thinking about x approaching 0 from the left. We don't care what's happening way over here to the left of x equals to 0. Like there's a lot of stuff happening, right? What we're talking about is as x approaches 0, like very much in the neighborhood of 0. So like thinking about creating an open interval around 0, so from the left, it seems like the function is approaching. So if we're approaching, x is getting closer and closer to 0 from the left-hand side, it seems like the y values for this function are approaching -2. Again, we don't care what's happening over here. Like we can see there's a jump in the graph over here, there's a vertical asymptote, there's a lot going on. We just care about in the neighborhood of 0. Directly, so going directly to the left of 0 and then approaching 0 from the left-hand side, it seems like that function is approaching -2. B is asking about the limit as x approaches 0 from the right. So again, we don't care what's happening way over here. we're thinking just to the right of 0. As x approaches 0 from that right side, it seems like the function is also approaching -2. Do we see that? So we would say that the right-handed limit would also be equal to -2. Now you can look at the graph again to confirm that as x approaches 0 from the left and the right, the function is approaching -2, or since we looked at the left-handed and the right-handed limit, those two limits both exist and they agree with each other. The two-sided limit, therefore, has to be equal to -2 as well. Okay. D, as x approaches 2 from the left. So going in the neighborhood of 2 from the left, as x approaches 2, it seems like the function values are approaching 2. Do we see that? If we don't see it, let's talk about it more. As x approaches 2 from the right, the function seems to be approaching 3. So I don't even need to look. The one-sided limits both exist, but they don't match. They're not equal to each other. Therefore, the two-sided limit as x approaches 2 is what we refer to as DNE, does not exist. It would be wrong. I'm going to erase the equal sign here, and I should just be writing DNE, which means does not exist. Thank you, Lindsay Lohan.
Yeah.
The limit does not exist. It means that the function is not approaching one single value as x approaches 2 from the left and the right in this case. It would be wrong to say, or inappropriate to say, that the limit equals DNE. You should not have equal signs when you're saying a limit does not exist. Okay, so any questions on those? Now we can also see what happens graphically at x equals to 2. A jump, which is a discontinuity. What type of discontinuity? It is a non-removable discontinuity. Okay, so we can see there's a jump in the graph. So it makes sense that those one-sided limits don't match up because we can see there is a jump in the graph. If Super Mario were running along there, he'd have to jump. As x approaches -2 from the left. So as x approaches -2 from the left, this arrow indicates that the function is approaching -infinity. A limit only exists when a function is approaching a finite number. Infinity is not a finite number. It's an infinite number. However, in this case, whenever a limit is DNE because it approaches a specific infinity, it's understood that we say the limit is equal to whichever infinity that the function's approaching. So like I would actually say this limit is equal to -infinity. However, the limit is technically DNE. But by putting -infinity, like that the limit is equal to -infinity, it gives us a description or an understanding of how the limit fails to exist. So the limit is technically DNE, and it's because the function values, the y values are trending towards negative infinity. Now, as x approaches negative 2 from the right-hand side, the function looks like it's trending towards negative infinity again. So still DNE. Neither of the one-sided limits technically exist. So the two-sided limit definitely is DNE. But because the one-sided limits are approaching the same infinity, we can also say that the two-sided limit is equal to negative infinity. Now, if we had something where there was a vertical asymptote and the function was approaching different infinities, I don't know, we could even just look at like 1 over x, right? So for 1 over x, like the limit as x approaches 0 from the left of 1 over x would be equal to negative infinity, which is DNE. And then the limit as x approaches 0 from the right of 1 over x would be equal to positive infinity. But if we're talking about the two-sided limit, as x approaches 0 for 1 over x, all we would be able to say is DNE. Like we couldn't say equals, like the infinities don't match up. And that tells us something about the function's behavior at x equals to 0. Okay, so everybody has their calculators out? So go ahead and in your y equals, type in this function. So x minus 3 divided by the square root of x plus 2 minus root 5. If you're using parentheses, make sure you have the appropriate parentheses. Okay, and then I go over to the table. Now this limit is asking us what's happening to that function as x approaches 3. So I'm going to put 3 in the middle, and then I'm going to choose values that are directly to the left of 3 and directly to the right. Like I probably wouldn't want to use like -1 and 0, or like 1, 2, 3, like 0, 1, 2, 3, like not close enough. So what I would do is like 2.9, 2.99, 2.999, 3.001, 3.01, 3.1. And then typing these values into your table. So for like 2.9, I get 4.4497. For 2.99, I get 4.4699. For 2.999, I get 4.4719. 3 is undefined. 3.001, I get 4.4724. 3.01 gives me 4.4744. And 3.1 gives me 4.4944. And if we peek at the graph, I'm just going to do Z standard. So if I hit the zoom button, number 6, to check out what the graph looks like. Interesting. Kind of just looks like a radical function. So looking at the graph, does it look like if you were just looking at that graph and I didn't give you what the function was, would you think there's a discontinuity at x equals to 3? No. But we know from looking at the table that there is a discontinuity, right? So that means that we would say that there is a hole at x equals to 3, which we know, right, aka a removable discontinuity So if we were trying to determine what that limit is by looking at the table, it seems like, so from the left-hand side, right, as x approaches 3 from the left, what does it seem like the function values are trending towards?
4.4722%.
Something like that, right? Because then from the right-hand side, I would go with 4.472, right? Because this digit seems like it's decreasing, right? Or like the values seem like they're decreasing. This seems like it's increasing towards 4.472. I would go with that as the approximation. Now, I can tell you that from evaluating this limit analytically, which we'll get to probably at the beginning of next year, like the first thing next year, that this ends up being equal to 2 root 5. And if you type in 2 root 5 into your calculator, you see an approximation of 2 root 5 is 4.472. So this is what I mean by like we're estimating either numerically or graphically. We'll be more precise with what a limit is once we're evaluating using either algebra or calculus. And when I say calculus, I mean like using derivatives, something called L'Hopital. So this limit exists. We were able to determine an approximation for this limit or estimate the limit by reading the table. Piecewise function. Piecewise. Now, if you remember how to type a piecewise function in, don't our calculators let us type in the piecewise? I forgot about that. Okay. Everyone always gets confused here with what's like, there's a comma, so the limit we're first trying to estimate is the limit as x approaches 0. So in your y equals, you can either type in each piece there, or you can pull up, what is it, math. B is piecewise, like if you arrow up, and I want a 3 pieces. Does everyone have that now on their calculator? I hit math and then I arrowed up to where it says piecewise, and then you pick for there to be 3 parts. So then typing in sine of x for whenever x, and I would hit second math to get the less than symbol. And then 1 minus cosine of x. Oh, do we have to split it up or can we do the compound inequality? I think we might have to do an and statement. So I would probably type x, here, I'll write it up here in a second, just let me check. X greater than or equal to 0. And x less than or equal to pi.
Where did you get ants?
So the way that I would type this in is, so you have y1, right? You have the rule, so sine of x, and then you do x less than 0, and you hit second math, and you choose the correct one, and then 1 minus cosine of x. You would want to type that in as x less than or equal to, x greater than or equal to 0. And then to get the and, you're going to hit second math, and then you'll arrow over to logic. Okay, and then x less than or equal to pi, and then cosine of x for x strictly greater than pi.
Second math. Wait, where's logic? You arrow.
So you go second math,
Oh.
and then arrow over.
Whoa, there's a word on my calculator.
Were we able, does anybody need help with typing in the piecewise, you guys?
Is it supposed to be these little lines?
Oh, are we, check your mode, make sure you're in radian so you have rad time.
I think we might have supposed to, we're just typing to y equals.
Yeah,
Well, that's
where'd you type it in?
That's kind of funny.
Can you does it work to like?
You can't copy and paste, we're just gonna struggle through this.
Sorry.
Wait, what's the function for the piecewise?
Oh, math, and then arrow up,
Okay.
piecewise.
Having to type my calculator is like ridiculous.
Okay, so once you've actually successfully typed in the piecewise, then you can use the table to fill in this. How much time do we have? We're okay on time, right? I'm gonna give everyone a minute to finish typing that in. Okay, and since this first limit is asking as x approaches 0, I'll do 0 in the center here, and then I'm going to do negative 0.1, negative 0.01, negative 0.001, 0.001, 0.01.1. So then for filling in the values, Oh, it's scientific notation.
Yeah. Is that
Times 10 to, well, it's up to you. You have to understand what that value means, right? So like the 5 times 10 to the negative 7th means you're moving the decimal place back 7 to the left 7 places. So 0.000000. I lost count on the number of zeros I have, but 6 zeros in 5. Now, as x is approaching 0 from the left, those values for the function seem to be increasing towards 0. Do we see that? Like as x approaches 0 from the left, it seems like these function values are increasing towards 0 as well. And then as x is approaching 0 from the right, the function values seem to be decreasing towards 0. And in this case, the function value is 0. So this is an example of that first case when the limit exists, where the function is actually, like the function value matches what the function values are trending towards, like matches the limit value. Okay, for pi, I'm going to put pi in the center. I'm going to do like 2.9, 3, 3.1, 3.2, 3.3, 3.4. If we type those values in, we get 1.971, 1.99, 1.9991, 2, negative 0.998, negative 0.987, negative 0.967. Does it seem like as x approaches pi that the function h is approaching the same value on the left and the right? Like the limit, if we think about the limit as x approaches pi from the left, what does it seem like h of x is approaching? 2, okay. And then if we think about the limit as x approaches pi from the right, yeah, it seems like h of x is approaching negative 1. Okay, even though the function value is 2, from the right-hand side, we're paying attention to what seems like h of x is trending towards. So those one-sided limits are not equal to each other, meaning, therefore, the limit as x approaches pi of h of x is dne. And if you look at the graph, the one-sided limits both exist, but they're not equal to each other. And if we look at the graph, what happens at x equals to pi? There is a jump. Which is what type of discontinuity? Right, so there is a jump in the graph. At x equals to pi, which again is a non-removable discontinuity. Okay, so this was an example of where the limit failed to exist. Notice whenever there's been a removable discontinuity, so a hole, and we saw this up here, right? So when there's a removable discontinuity, the limit still exists. But if there's a non-removable discontinuity, it seems like the limit fails to exist. Is D&E? Here's Lindsay. Okay, so let's look at some other examples of when a limit fails to exist, or when you would say the limit is D&E. So this first example, piecewise, is whenever there is different right and left-hand behavior, which we just saw in the example above. Oh, there's a typo here. This should be x greater than or equal to 2. So you can go ahead, this is good practice for typing the piecewise into your calculator, and then you can fill in the table. So hit math and then arrow up to piecewise. There are only 2 pieces for the function g of x. Okay, typing in the rule, x, and then to pull up the less than, hit second math. And then second math to pull up the x greater than or equal to symbol. And then it's easy to go over to the table and filling in, I've given us the x values, so filling in, although you could technically do this one like in your head, right, for the, whenever the function is x, the identity function, 1.9, 1.99, 1.999. Okay, but then if you type in 2, and you could do this in your head as well, g of x is equal to, or g of 2 is equal to 4, then 2.001, we get 4.004, 2.01, we get 4.0401, 4.41, okay. So we're trying to evaluate the two-sided limit for piecewise. It's important, especially whenever the limit you're trying to take and there is where the domain switches, the domain of each piece switches, you want to think about considering the one-sided limits. So like the limit as x approaches 2 from the left of g of x, we can see in the table, it seems like g of x is approaching 2. But then the limit as x approaches 2 from the right seems to be approaching 4. So those limits are not equal to each other, and therefore the limit as x approaches 2 of g of x is D-N-E. And this is a function you guys know how to graph by hand. Like you know that there would end up being a jump in the graph at x equals to 2, right? You'd have to lift your pencil if you were tracing the graph, which is a non-removable discontinuity again. Questions?
In this case, like the left-hand side and right-hand side limits both exist. It's just that the combined limit doesn't, right?
Because the left-sided limit and the right-sided limit both exist, but they're not equal to each other.
Yeah, so
the two-sided limit is D&E.
Yeah.
Okay. Limit as x approaches 0 of 1 over x squared. Now thinking about this function, so you can type in the 1 over x squared into your calculator if you want. But like you could also think about just what would happen if you're plugging these values in your head. So for 1 over x squared, like if you plug in -1/10 in for x, and you square it, it's a small number, but then because it's 1 over that really small number, it actually ends up being a kind of bigger number, right? So 100, 10,000, 1,000,000, undefined, 1,000,000, and symmetric to the left and the right, these values. Even function. Okay. So if we think about as x approaches 0 from the left and the right, you can think about the one-sided limits here, but we can also see that it seems like the function values are symmetric to the left and the right of 0. If we kept choosing smaller and smaller values, like closer to 0 from the right-hand side, or I guess technically larger and larger values to the left of 0, what would be happening to those y values, those function values?
They'd be going to
Yeah, they would continue to get larger and larger and larger. When you square them and then you're taking the reciprocal, they would continue to get larger and larger and larger. So we would actually say that this limit is g and e, but it's g and e because we can say the limit is equal to infinity. Okay, so d and e, and it's because the function is increasing without bound. I'm like combine without. Whenever the function is approaching positive or negative infinity, as x approaches a number, graphically, what do we interpret that as? A vertical asymptote. There's a vertical asymptote. I think this next one is a good one for us to kind of use as a warm-up next time. So I'm going to end there. You guys do have some homework.